Hello, everyone, and welcome to another wonderful day of physical chemistry. So, today we're going to pick up where we left off, talking about computational methods by going from the semi empirical methods to a true quantum mechanical approach, the simplest of which is called Hartree-Fock. So, Hartree-Fock, like so many of the other uh, quantum mechanical methods, focuses on trying to solve the secular equation. Now, it works on a modified form of the secular equation called the Fock matrix. So, first of which, the thing that I want to emphasize is that when treating the overlap integrals for the Fock matrix, these are actually solved explicitly. So, we construct a set of our orbitals and we actually mathematically determine the extent of overlap in these regions. So no shortcuts with solving the overlap integrals. These are solved explicitly. So this will slow down our system a lot as we're going to have a lot more off-diagonal elements we need to treat. So this leaves us with the last pesky problem. How do I solve my Coulombic and my resonance integrals? So the first thing we do is instead of treating the system with a full Hamiltonian, we use what are called the Fock matrix elements. So these Fock elements start by saying, I'm going to solve the true Hamiltonian for a single electron in the given orbital or orbital overlap region with a static field of all of the other electrons in the system. So it does this by setting up the system in a series of matrix elements. So the first term of which essentially is going to focus in on kinetic electron energy. So this is going to be the kinetic energy of the electron in either the overlap region, if mu and nu are different, or in the actual straight orbital, if mu and nu are the same. Similarly, I can also then examine the attractive portion of the potential to all other nuclei. So we're summing over the interaction where K is all the other nuclei present. So ZK is going to be the strength. And then simply by correcting for the distance of my electron from the nuclei, I should be able to come up with the net attraction of the electron in this region to all of those nuclei. Now, it's this third term that's the real stickler for most computational methods. This is that good old electron-electron repulsion term. And this guy's going to be the trickiest one to solve. So let's go ahead and examine what all of these matrix elements, elements look like in a more traditional integral form. So nothing's too surprising occurs with our electronic kinetic energy, as this is simply going to be applying our gradient to a certain wave function and then integrating over all space with respect to the second wave function. So here, we're really going to be taking advantage of the Hermitian nature of these operators, as it doesn't matter whether we're doing mu nu or nu mu, as these will simply give us complex conjugates of each other. And since the kinetic energy should be a real value, we don't even need to worry about the complex conjugate. They'll simply give us the same value. Now, the second term, well, this one also isn't too surprising. It's just going to be dependent on the inverse, the electronic attraction will be just dependent on the inverse of the distance in between the electrons that I'm examining and the given nuclei. So this isn't too bad, but it is worth noting that this is going to be a lot of integrals to solve. So mathematically, this becomes quite cumbersome, but conceptually not too difficult. Now, this last term is the real kind of tricky bit, as this is going to be the electronic repulsion. So note we have a positive term here indicating a repulsive interaction. Now, this is going to be the electronic repulsion in between the orbital I'm looking at, so this overlap region of mu mu nu, with every set of orbitals. So we're going to do a sum over all other low orbital overlap regions, lambda psi. So this generates what's called a four-centered integral, as we're going to deal with the interaction between electron 1 in the overlap region and electron 2 being on the other overlap region, and then looking at the distance in between the two systems, and then integrate over all space for first electron 1 and then electron 2. So this is quite a hefty set of integrals, but it should give us the electronic repulsion because that is going to be proportional to 1 over the distance in between the two electric charges. However, we do run into a pesky little feature here, which is the fact that since I'm looking at the interaction in between the electron on these orbitals and all other orbitals, we have to deal with the fact that it turns out that these electrons are indistinguishable, which means that when I'm treating the system, at some point, I will have treated the reverse, the interaction with these orbitals and my original orbital. So we have this pesky issue of double counting, and we can correct this via what's called electronic exchange. So I subtract out some of the electronic interaction, where I essentially mix up the orbitals of the orbital overlap region in between the first two sets of orbitals and the second two sets. Now, by doing this, subtracting out the second integral, we reduce any possibility of double counting. However, there is one pesky little feature. I'm looking at the interaction of my electron in orbital 1 with all other orbitals. Not all of these orbitals are occupied. And that's where this p term comes in here. So this p term is essentially going to be a matrix which simply sums up how occupied any given how occupied the atomic orbital lambda is by summing up over its contribution to all of the occupied molecular orbitals. So it turns out that if I say have an electron or atomic orbital that contributes to a bonding and an anti-bonding orbital, the atomic orbital would be 50% occupied. And so by accounting for this, we can essentially correct to make sure that I'm not including any interactions or repulsions from orbitals that aren't actually occupied, which should thus help give us a better repulsion energy. So using these sets of equations, we can then go ahead and solve for the Fock energy for either our resonance or Coulombic integrals. And then using these individual solved matrix elements, we can then insert them into our secular equation and then do a whole bunch of fancy matrix algebra to back out the true energy of the system. Now, using the variational principle and some rather more complicated mathematics than we've shown so far, you can actually use a computer to calculate the lowest possible energy value, and this should give us the true orbital configuration. However, one of the key things that that's very important is you'll notice that all of these elements look at the overlap regions in between a certain set of orbitals. Now the question is, what orbitals am I actually going to use? We're actually going to change our language a little bit here, and instead of actually calling them orbitals, we're going to call these basis functions. So what mathematical functions am I going to use to build up my true molecular orbital density? Now, this is a big driving force of computational chemistry. So the traditional approach, and the one we've used so far, is I build my molecular orbitals out of my hydrogenic orbitals. So my hydrogenic orbitals follow what's called a Slater type orbital, because I have my big functional, which has a dependency on R theta and psi, or theta and phi. Now, it's worth noting that theta and phi aren't really going to change under most of the manipulations, as the angular components stay relatively fixed. But the radial component is going to be the one that's most affected by these interactions. Now, one of the other features that I have to also worry about is that, well, it turns out that my radial component has a polynomial expression, and then most importantly, an exponential one. Now, this exponential decay term is really hard to integrate computationally. So instead, what we do is we traditionally switch out this Slater type orbital for a much more easy to integrate Gaussian type orbital. So the big thing here is I switch out an exponential of r to an exponential of r squared, which becomes a lot easier to integrate. However, we do run into this pesky problem of the density is going to be of a slightly different shape. So I want to build up a set of Gaussian type orbitals, or GTOs, that look exactly like a single Slater type orbital. So in practice, the easiest way to do is I'm going to build them up out of a linear combination of several Gaussian type orbitals to generate a density that looks just like a Slater type orbital. So the simplest form of this basis set is called STO3G. So I use 3 Gaussians, all of which have fixed coefficients, so I don't let these coefficients to change as I switch in between molecular systems. However, they are parameterized to work best for any given atom to generate, say, the Slater type orbital for that atom. So I'm going to have a certain set of coefficients for carbon to make it look like a carbon Slater type orbital, like whether it's a p or an s orbital. However, I don't let these coefficients change. So I have a fixed orbital, which does a pretty good job of replicating STO. However, there is some issues at very short distances. However, since most of our electronic interactions are in this wider region, we accept this as the cost of doing business. However, one of the things that's worth noting is that while this does actually accurately represent the atomic orbitals, we should ask our question, are the atomic orbitals even the best basis set to use? Because the atomic orbitals don't have the true flexibility I need to represent a good electronic density. So I can actually probably model my molecular orbitals a little bit if I allow these coefficients to change. However, these coefficients won't really change for any of my core electrons, so I'll keep those coefficients fixed for my core electrons, but I'm going to allow them to vary for my valence electrons. So if I've got my valence electrons and I split them up into 2 groups, say I've got one set that has fixed density and allow this third one to have a coefficient that changes the ratio, so I could have more of this character or less. This will actually give me a certain amount of flexibility, as I can allow if I add in more of this third character, I can allow my orbital to stretch out. If I reduce the amount of character, I can let it pull in. And this basic idea is called double zeta. You can, as I have 2 groups. You can also have functions that have triple or even quadruple zeta, as I allow a lot more flexibility in my basis set. However, the more flexibility I allow, again, the larger the matrix I have to solve, because I'm going to have more contributing orbitals, and the slower the calculation becomes. So when choosing basis set, this is the classic balance. If I go to double or triple zeta, more accurate, but it also takes a lot longer to perform the optimization, as I have many more matrix elements to, first of all, perform the integrals on, and second of all, to actually even just orthogonalize the matrix to get my energies. So again, we get hit twofold on this time component. So let's do a quick summary of HartreeFock. Turns out it's actually a fairly accurate method. It tends to have errors of, say, less than about 10 to 15 kilojoules per mole. So or sorry, 10 to 15 kcals per mole. So it isn't a perfect method, but it gives us pretty good qualitative descriptions. And it allows us a fairly simple way of building our molecular orbitals by assuming that all of the other molecular orbitals are rather fixed. And we can build our molecular orbitals out of a fairly flexible linear combination of our basic atomic orbitals and get a little bit of more flexibility by using Gaussians to build up a more flexible version of our atomic orbitals. Most importantly, it perfectly treats the indistinguishability of electrons, so it allows electron exchange, which is a fairly hard phenomenon to encapsulate and is an important quantum mechanical principle. Unfortunately, it turns out there's a lot of things that HartreeFock doesn't do a good description of. And we pretty much come up with a whole class of properties called correlation. Now, it is worth noting that the strict definition of correlation is anything that HartreeFock does a bad job of. However, we split it up into two major categories, dynamic and non-dynamic. So dynamic correlation is focusing on this fact that we're building up our Fock matrix by assuming that electrons don't move. I have a static field. I have no coordinated movement. And as a consequence, it tends to miss a fair bit of things, such as, well, anything like London dispersion, where I have induced dipoles, because induced dipoles are electronic movement. So it can do a fairly poor job of a lot of those intermolecular properties. Furthermore, it also does fairly poorly on what's called non-dynamic correlation. So non-dynamic correlation focuses on the fact that I built up all of this, I optimize my orbitals by assuming that I have a single set of molecular orbitals that perfectly describes my system. However, I have to worry about the fact that in truth, my orbitals may be composed of a linear combination of molecular orbitals. All of my molecular orbitals may not be perfectly occupied. They may be partially occupied. And this is a fun phenomenon that we've seen several times before, where I have single electrons spread out over degenerate molecular orbitals or near degenerate molecular orbitals. So as a consequence, if you've got more non-dynamic correlation, which is very common in conjugated pi systems, the bigger they are, the more present it is. But most importantly, in metals, which have so many d orbitals so close in energy that the non-dynamic correlation can become a major player. And in these cases, turns out HartreeFock doesn't do quite so well. So in order to describe these systems, we need a slightly better computational method, or at least a more flexible one. And so for that, we often turn to DFT, or density functional theory, which we'll spend more time talking about next time. Until then, take care.